Factoring by grouping.
I'm writing part 2 in my notes.
Can I just say this is really cool recording? Like the angle, yeah.
I'm glad because, you know, the artistic nature of it is important to me as well. Factoring by grouping. I had an interesting conversation with Artur about this yesterday, actually. He was asked about what this stuff is used for in real life. The shortest answer I can give is that these polynomials are used for many things. A lot of them actually describe motions of heavenly bodies, a lot of stuff in physics, and...
Nobody's majoring.
Well, regardless, at any rate, there are uses for them. However, these patterns we're learning right now, like sum and difference of cubes, they only work with a certain type of very neat and pretty polynomial, which will never describe anything in nature. However, these factoring patterns often show up on standardized exams.
Oh, cool.
So this is literally... So what is this used for in real life?
Nothing.
To get into college.
It's just an arbitrary thing that was made up and decided to use.
Yeah. So I won't lie. The specific things we're doing right now
Are irrelevant.
Have no practical applications.
Well,
of a degree.
they are a little bit of puzzle solving. You know, there is a little bit of building up your mental muscles in general, but no one, I don't think any astrophysicist has ever come across a phenomenon where the numbers were so nice and neat that sum and difference of cubes really helped them.
Well, you never know.
You never know, it might happen. Okay, factoring by grouping. This is something that comes up only in another rare type of puzzle, Rodney, which if you can't recognize, Rodney, you will fail the next test. So, please pay attention to it so you can see it. Now, for factoring by grouping to work, you have to have 4 terms. Okay, and these 4 terms have to have a very special property. The 4 terms have to be able to be split between the first 2 and the second term, 2, and have a common factor. That was not said very clearly. I apologize. Let me go on to the example. What is... Get rid of it. What is the greatest common factor of the first 2 terms?
X squared.
X squared. And what's left after I take x squared out of the first 2 terms?
X plus 3.
X plus 3. What is the greatest common factor of the second 2 terms?
10.
And what's left after I take 10 out of the second 2 terms?
X plus 3.
X plus 3.
So everything, they're both X plus 3 where they have the...
Yes. Now, this will not happen with every third-degree polynomial of 4 terms. It only happens with some of them. Okay, so the trick is to be able to spot this so that you know this shortcut exists. We're going to learn some longer ways to factor polynomials. I pulled x squared out of the first 2 terms, and I factored a 10 out of the second 2 terms.
Oh, will this happen on our homework tonight? Like this?
Yeah, and I noticed that I have x plus 3 left in both cases. Now, what happens from here is x plus 3 is now a common term.
So it'd
Okay.
be squared.
Well, it's not squared. X plus 3 is a common term, so what I can do is I can pull x plus 3 out as a common factor, and I'm left with x squared plus 10. I pull the x plus 3 out of both terms, and I'm left with the x squared and the plus 10.
Why can't you have X squared?
But you forgot the other x3.
I didn't... I love that question. That's actually a very smart question, but it doesn't actually work that way. No, it's good. Okay, Jordan, let me go back. If I have 5x plus 5y, Jordan, what does that factor to? What can I pull out of both terms?
5.
And after I do that, do I pull out 1 5 or 2 5s?
Well, I mean, I get. Oh, because what did you foil it?
Well, it's not really foiling, is right?
No,
It's like
not
it's the reversing the distributive property. Okay, but you see how in this case there are 2 5s.
Yeah, but you can't just like make numbers disappear.
Well, you kind of can in one sense. Like for example, if I have 5 hamburgers and 5 French fries, how many Happy Meals do I have? 5. I've got 5 burger and fry meals.
That's not what we're talking about.
Well, it kind of is. If I have the same thing being multiplied in 2 terms, I only pull it out once, no matter how many different terms it appears in. And it's not really making numbers disappear.
Because you're still multiplying all the things by that.
Yeah, it's the reverse of the distributive property. Like if I distribute this, I get multiple. Jordan, I have an example. I'll want to talk about that more. But for now, Jordan, can you trust me that the x plus 3 appears twice, but you pull it out and it only appears once? And after I do a few more examples of this, I'll go into more detail with that if I have time. So that's actually a concept that I really like. Okay, so this is how factoring by grouping works. You have 4 terms, and you notice the first 2 have a common factor, the second 2 have a common factor, and when you're done, you have the same thing left after you pull it out.
Will that always be the case?
No. And in fact, on the test after this one, I'm going to give you a bunch of them that look like this, and some of them will be able to be solved this way, and others will require a longer way to do it. So it's going to be to your benefit to notice this shortcut. Okay, another example of factoring by grouping. And I need one that has some subtraction in it. Steal it from the book. That's too much subtraction. That's the right amount.
I'm kind of starting to get it now, because you see it in a better light.
No, it's like Goldilocks.
Never mind.
No, I was interested, actually.
Because now, I'm trying to figure out the best way to explain it. Like, you know how when you factored it, now I see it as like you make it into polynomials that can be distributed.
Right, it's the reverse of what we were doing 2 nights ago.
Yeah.
Good, that's a good way to look at it, Brian.
What do you need to know?
Okay, now, what is the greatest common factor, again, of the first 2 terms?
Oh, 3.
3 and what else, Amanda?
X squared.
3x squared. So that's going to be 3x squared. What else is left? What's left now?
X.
Two.
X minus 2. Okay, now this is a little bit interesting here. What do we have here?
X minus 2.
X minus 2. So what is the greatest common factor that we can pull out of X minus 2?
You're going to make it disappear.
Sort of, not quite.
So you want X and X 1.
1. It's actually 1. The greatest common factor of x and negative 2 is 1. So here's a really rare case. I have to factor that 1 out and have x minus 2 left. So it's not quite making it disappear, Jordan, because there has to be a plus 1 left.
But you're going to make it disappear.
Well, now I am, yeah, because now I'm going to pull the x minus 2
We can tell you what it's going to be.
out of, and I'm left with 3x squared plus 1. Okay, any questions on that?
You can do finger puppets.
Just that after that, then we do what we learned earlier, the polynomials. Like
Sometimes you can keep going, sometimes you can't.
I have a question.
Yeah. Archer, you say that in the middle of every process we learn.
Wait, what? So after you take out that x minus 2, you're just left with what's outside the front?
What's outside of each parentheses, yes.
Okay, and then
Right.
you put that.
Yeah. Yasmin?
I'm confused. How did you get 3x squared?
Okay, we looked at 3x cubed minus 6x squared, and we said, what's the greatest common factor between them? With the 3 and the 6, it was fairly easy, because we had 3 is the largest number that divides evenly into 3 and 6. Okay? And then we asked ourselves, how many x's did we have being multiplied in each of them? Well, we had 2 x's being multiplied here, and 3 x's being multiplied here. That means we can pull out the x with the larger exponent. Okay, see if we multiplied this backwards, if we distributed it, 3x squared times x would get us 3x cubed. 3x squared times minus 2 would get us the minus 6x squared. Sometimes seeing it how it distributes back is the easiest way to see how to factor. There's one more example of these that I want to find, because there's one type. Your book's got to have one in here. There it is. Okay.
Can you leave that up for a moment?
Yes. Because we have to pull a factor out of these two. If we didn't, it wouldn't work distributing backwards there. Okay? If we didn't have this plus 1 here, I mean, it's my standard answer for factoring, and it's not the best one, Artur, is if you can redistribute back and get the same thing, then you factored correctly. If we multiply 1 by the x and 1 by the minus 2, do we get back to here?
Yeah.
Then this is the correct factoring.
Why is it 1?
Because we have to pull something out of them. In order to be able to pull x minus 2 out of so what we have now, Artur,